In this video, what we're going to do is we're going to do a very brief refresher of the topic of trigonometric graphs. Now, trig graphs are something we covered when we did National 5 Mathematics, and they're something that does come up occasionally at a higher level, so it's worth a look back. What we're going to talk about is the basic shape of the three basic trig functions, your sine, cos and tan. We're going to look at some of the key properties involved with each of these graphs, and we're also going to look at transformations, how the graphs can transform, what can change about them, and how we can do that. Now, graph transformations were covered in an earlier video, so if you also want a refresher of it, go back and look at that as well. Now, the basic trig functions, your sine, cos and tan, all have a set shape, and they all look just like this. So your top graph here in the top left, this is your graph of y equals sine of x. So it's a wave function that starts at 0, reaches a peak value at 90 degrees, goes back to 0 at 180, its minimum value at 270, and its peak, it goes back to 0, at 360. Y equals cos x, similar shape to the sine curve, a nice wave, but it's off, i.e. sine's maximum was at 90, cos's maximum occurs at 1, so it's essentially shifted left 90 degrees. General shape stays the same, it's got a maximum here at 1, minimum at -1, back to maximum again at 1, cuts the x-axis at a couple of other points as well. Then we've got the y equals tan x. Now tan x is a graph that looks like this. It shoots off up towards infinity here, below 90 degrees, but then at 90 degrees we've got a discontinuity. Tan never ever reaches a value at 90 degrees. We'll talk about that in just a second. It then goes down to minus infinity just above 90 degrees and works its way back up through 0 at 180, off to infinity again by 270, again where there's another discontinuity. It then continues this repeated pattern over and over again, with discontinuities occurring every 180 degrees from the 90. So there's one at 90, there's one at 270, there's one at 450, and it keeps going on and on and on like that. Now it's actually quite easy to explain. Tan x is given as a relationship between sine and cos. Tan is actually given as the relationship of sine x over cos x. That's how you can calculate it using those two. Now, at 90 degrees, if you look at the cos graph, cos at 90 is 0, and cos at 270 is 0. So essentially, every single one of these points here, you've got some number on the top divided by 0. And when we divide by 0, well, that can't be done. So that's why these discontinuities appear in these two spots here and continue to appear every 180 degrees. It's due to the periodicity, i.e. the repetition, of the cos x graph. Now, there's two key things that we have to be able to discuss about these graphs. One is something called the period, and the other is something called the amplitude. Now, the period of the graph tells you how long it takes to repeat. Okay, so how long it takes to repeat itself. So if you look at the graph of y equals sine x, it repeats itself every 360 degrees. So does cos. When it gets here, it's going to go the same pattern again, then the same pattern again, and sine will do the same. The period of just a standard sine and cos graph is given as 360 degrees. However, if we have cos ax or sine ax, what this is going to do is change the graph in a way, and we're going to talk about that in just a second, but essentially the way to think of it is it changes the number of repetitions it does in 360 degrees. So to get the period of any one of those, it's 360 divided by a, and that'll tell you how long it takes to repeat the graph. However, tan's different. If you look at tan, it only takes 180 degrees before it repeats itself. So tan takes that. So for the period of tan, it's actually 180 divided by a, because the same logic, if we had tan of ax, would occur here. It would repeat itself, it would stretch or squash in the x direction, just like graph transformations were covered before, and it would repeat 180 divided by a. Now the amplitude tells you about the height of the graph, so it tells you about the height from the top here to what would equivalently be this axis here. Now a graph like this, you know that the amplitude is 1. Easy way to get it, when you've got just a generic function that has different highs and lows, so not 1 and -1, the easy way to do it is take the maximum value, subtract the minimum value from it, and then divide your answer by 2. So say our maximum was 6 and our minimum was -2. We do 6, take away -2, so 6 plus 2 gives me 8, divide it by 2, that would tell me that my amplitude is 4. So the distance from what would be the centre line here to the top, or the centre line to the bottom, would be 4. Now these key properties are properties we can calculate for any of the trigonometric functions. So we can calculate the period of cos, sine or tan, and we can calculate the amplitude of cos and sine. However, the exception to everything is the amplitude of tan. Because tan goes off to infinity in the positive direction and goes down to infinity in the negative direction, we can't physically calculate its maximum value or minimum value, so we can't find the distance between them, so we can't find the amplitude of tan. That's our only exception to any of these properties that we're able to calculate. Now, working with all the properties of trig functions and the general appearance of them, we're able to do transformations in relation to each of these trig functions. The next video that you'll see will cover how these transformations work and what they'll do to the graphs themselves.